All right, so we're going to solve this differential equation using Laplace transforms. And this is an equation you can solve without a Laplace transform, but the point is to, learn how the transform works. So we're just going to take the Laplace transform of both sides. And when you do that, Laplace transform is an integral, right? So you can split this into three integrals and you can factor out constants from integrals. So this becomes, three Laplace transforms. And then you take the Laplace transform of the right side. Now, the Laplace transform of zero is just going to be zero. In fact, I want to give myself more room there, so I will wait to put that zero down. So now we're going to use our table of Laplace transforms here, and we need these two at the bottom. So the Laplace transform of a derivative can be written in terms of the Laplace transform of the original function. And same with the second derivative, you can write it in terms of the original function. So the Laplace transform of y double prime is going to be this s squared. Let me just write this down. S squared Laplace transform of y minus s times y of 0 minus y prime of 0. So that's a Laplace transform of y double prime. Now we're going to do the Laplace transform of y prime. And that's going to be s Laplace transform of y minus y of 0. And then we also have plus 2 times the Laplace transform of y. And then that's equal to 0 since Laplace transform of 0 is 0. All right, so at this point, we can plug in our initial values. So y of 0 equals 0. So we could just go through and get rid of all the y of zeros. And then y prime of 0 is equal to 1. So this guy is going to be 1. So I get s squared Laplace transform of y. Don't have this term because it's 0. And then minus 1 minus 3s Laplace transform of y plus 2 Laplace transform of y. Again, I don't have this term because it's 0. Okay, at this point, you want to move everything to the right that does not have the Laplace transform of y as a factor of its term, okay? So I'm going to move this 1 to the right side. So I'm going to add 1 to both sides. And then from whatever's left, I'm going to factor out the Laplace transform of y. So I get s squared from the first one minus 3s plus 2. And notice those are the same coefficients that are in the original equation. And that kind of should happen here. So if that doesn't happen, you might want to go back and check your work. So now we solve for the Laplace transform of y. So we have to divide. Right, so what we want to do is to take the inverse Laplace transform of both sides, and that'll give us y, and that'll be the solution to the differential equation. If what's in the denominator on the right side, if that will factor, then you're going to factor it, you're going to split it apart and use partial fractions. So this one does factor. So what is it? It's going to be s minus 2 and then s minus 1, right? So we just need to take this rational expression here and split it up into two fractions and use the method of partial fractions. the partial fraction decomposition. So just kind of off to the side, we'll do that. So I'm just going to take this 1 over s minus 2, s minus 1. I want to set it equal to, say, a over s minus 2 plus b over s minus 1. And we just need to solve for a and b. So I'm going to multiply both sides by this denominator. That'll leave me with 1 on the left side. And when I multiply it times the first term, these s minus 2's are going to cancel out. So I'll end up with a times s minus 1. And then when I multiply this times the second term, I have to distribute it, right? So I'm multiplying it times both of these, and the s minus 1's are going to cancel out. And I'm left with b times s minus 2. So there's a couple of different ways you can go about solving this. Let's do it this way. Let's get rid of these parentheses. Let's distribute. And then let's group them together. In fact, I can factor out an s from the first two. And then I'll just say the negative a minus 2b are together. So we're going to just compare both sides. So I don't have an s term on the left. So you can think of that as being, like s has a coefficient of 0 on the left. Well, that means that, a plus b has to be equal to that 0. So that'll be one equation in my system. And then the constant here is negative a minus 2b. Well, that's got to be equal to the constant on the left, which is 1. So negative a minus 2b has to be equal to 1. So you're just going to solve this system for a and b. Looks like I can just straight up add these equations here. The a's are going to cancel out. Here I get negative b equals 1. So I know that b is equal to negative 1. And if I know that a plus b has to be equal to 0, that means that a has to be equal to positive 1, right? So now they add up to be 0. All right, so I know that this expression, 1 over s minus 2, s minus 1, is equal to 1 over s minus 2 plus negative 1 over s minus 1. So a is 1 and b is negative 1. So when I take the inverse Laplace transform of both sides, the inverse Laplace transform of the Laplace transform of y, well, that's just going to be y. And then I need the inverse Laplace transform of 1 over s minus 2. And we'll say minus the inverse Laplace transform of 1 over s minus 1. Then I'm going to use my table. So 1 over s minus a, if you take the inverse Laplace transform, that's going to be e to the at, right? So I'm just going to use that to say that y must be equal to, here, e to the 2t minus e to the 1t, or just e to the t. And that is your solution. You can check this with your other methods, but this should demonstrate how the process of using Laplace transform to solve differential equations works.